I'm supposed to be standing somewhere here. It's very bad idea because I never can stand still, but we'll see what happens. Almost everybody sitting. Okay, I start slowly. Welcome to Tech Angelist. It is a name that we sort of put together. It's supposed to be an evangelist with technology inclination. I hope you understood that without me telling you, but that's what it is. We're from Oracle, primarily, but this meetup and many of our other meetups are relatively product or Oracle independent. It's actually newer technologies, whatever is moving fast in the market. We try to have an idea, we try to learn it ourselves, and then we try to share it with others, basically. That is the idea. And today we're going to talk about machine learning, or actually one type of machine learning, which is reinforcement learning. That's why it's called reinforcing the path, very dramatically. We have had two other meetups earlier. The first one was reinforcing the path 1, and that's where we went through reinforcement learning, the formula and how it may be implemented based on code from Berkeley. It's course code, it's open for everybody, actually. And the second one was because there were a lot of people who were interested in reinforcement learning. The second one was because we received some informational requests related to a need for Python course. So we had the second meetup in the form of a 2 times 45 minutes course, crash course. I don't know what's faster than crash course, but the crashiest course I've ever done. It was Python introduction. And now that we assume everybody understands Python, we're going to go ahead with the second reinforcement learning part. But this is really a very fast summary of the first one. Sorry, Asker, you've seen this all, but then some of the people have been to the first one. Asker was actually the arranger of the first one. I mean, the time he's there, you can say hello to everybody. Yeah, that's and there are probably others who've been to the first one, who've seen this, or who've learned about this. We need to go through this. What I will do is take the reinforcement learning, which actually is Q-learning, and build build it up to a deep learning version using a neural network. So the first part is just good old reinforcement learning, path optimization starts actually, and then we'll put a neural network on top of it, under it, whatever you think is the best. And we will try to implement Q-learning with deep learning, which we call deep Q learning. Yes, these, as you probably saw, we have a little car in the end. This is the car, very ugly. I know, I'm not a very good car designer. And it has 3 sensors that it will sense the environment with. Basically, what we are trying to do is, she's the boss of my boss, so I can't say no. And my boss is sitting behind that. Let's see. Do you hear me? No? If you didn't hear me before, you still aren't hearing me. This is not working here. Let me just check. What are you checking? Anyway, I will try to talk louder, or the ones behind should move forward. Yeah, the technical expertise, the director of the technology group, the pre-sales group, is going to fix it probably from the way he started walking. Anyway, what I was saying, that we have a car and then there are 3 senses. The job of these 3 senses is basically to sense the sides, and we call it in this exercise, you will see why eventually, we will draw rows where the sides are actually sand dunes or collection of sand. So like when the car is running, it doesn't crash, it just slows down, but it can't climb over, but it will get a penalty for climbing over and slowing down. And what it is going to do is we're just going to let it go run. Implementing a neural network deep learning, Q-learning algorithm will let it run and experience, experiment, explore the environment and learn. And then eventually be able to find the way home easily. So this is an exercise which you will probably be doing physically after this one, that entails going from work to home. All right. This is our agenda. The pizza part is gone. We will be reviewing the algorithm that is related to reinforcement learning and Q-learning, because we'll build on that. And then we will look at the neural network and how we use the neural network around Q-learning, reinforcement learning model. And then we'll look a bit at the tools, and we'll just go through the code. If you have the chance, and if you downloaded everything that is in the page, the meetup page, I set up unfortunately pretty late today, or well, actually pretty late was today early in the morning, but that was pretty. I should have done that a few days ago. Sorry. And then we'll just walk through the code a bit fast, and we'll point out the important things in the code, which implements the stuff that we'll be seeing, the core of the stuff. There's lots of code that sort of does all other things, like creating a car. That's not what we're going to be interested in. It's not application development, but it is actually the neural networks we're interested in. So we'll look at that part. And I will, of course, give you a tiny little walkthrough, if we have time, of what the kind of artificial intelligence machine learning platform we offer, and that the ones that I prefer using, basically. Okay, that's the plan. This one. Yeah. So we walk through reinforcement learning fast, and the goal is now this is the setup, the way you should be thinking. Okay, we have Master Yoda, and he's in trouble, so we're going to run as fast as we can and go reach Master Yoda and help. There are blocking elements and enemies on the way. So this guy has to learn the correct path and then go save Master Yoda. The mindset when we are doing this kind of stuff is the grid. Because if you think of the whole screen, actually, it's like a grid. It's just pixels next to pixels. And this is a very rough screen. You wouldn't buy this one, but this is much easier to look at and understand when we're explaining the algorithm, basically. So we're going to look at how an agent starts from one point in the grid and calculates the risk of going this way or that way after some rounds of learning. That is what Q-learning is. This is the old stuff. So what the goal is, I just told you actually. It can be used in, this is the technique that's often used in creating intelligence to play against games as well. This is the kind of intelligence that you would use for programming either intelligent games or intelligence that plays the games, basically. So this is the kind of stuff. Let him step around with an algorithm of rewards for the right choices and penalties for the wrong ones. That's the idea. So what we're going to do is think of the world as a grid. Again, this is a grid. The next step is here, there, right? The next step could be here, but there's a wall there. It can't go there, so it has to, and it has to understand that it doesn't want to try to go in the wrong direction, or there are blockages in the walls or whatever. Okay? So what we do is we put a goal with a win reward that's very high and penalties around for doing wrong things, which are not very nice. Negative numbers, for example, for every time. We accumulate these in a sense. Okay? There will be, not all rewards will be one. Some of them will be much less. Most of the rewards, as you will soon see, will be in the form of negative rewards, penalties actually. Because whenever, think like this, whenever you take a step anywhere, you actually, as long as you're not getting close, or you're not on the goal itself, it is a penalty because you're not there where you should be. Okay? Which still, yes, much less penalty, maybe not -1, maybe -0.2, but it is a penalty that you're incurring. So most of the time you're surprised when you see that the reward is always, almost practically always negative. So we look at the start, there was this Bellman equation in the very, very old times, around 1957, here, as you see, and it says, and you think you're learning something new. A lot of these algorithms are based on quite old findings, and a lot of it is pure mathematics, operation, research kind of optimization kind of problems, and this is path optimization, basically. So we're going to look at the Bellman equation. It looks like this, okay? Does it look like this? I know that many people somehow mislike this kind of stuff because it is relatively hard if you're not used to looking at it and interpreting this kind of stuff. It's a bit hard at the beginning, but it's actually very easy. What we do here is we have a state, current state, and the next state. To which state you're in, what kind of reward you have received or penalty you have incurred in this state, and what will happen according to your learning when you step into the next one. So there are states basically we're talking about in each step. And then there are this value that represents each state and an action based on your learning of the value of each state, basically. And then of course those values are calculated based on your rewards at a state and the action you take. So the reward isn't only the state you're sitting in, you already collected a number of penalties and rewards when you're sitting in a state, not moving, but when you take the action, there's a reward or penalty. So the reward is a function of state and action. And then there's, of course, the probability of taking an action from a state and ending in another state. Okay? That's the last one, because your calculation will take into account whether you're taking this action of going from this state to this or there. It will not have the same value, especially when you're here and you're banging your head on the wall, right? They will have different penalties. So, you will be learning and adjusting the problem often. So, yeah, that is the Bellman equation. That's the value or utility or expected benefit at a current state. You're going to be taking the maximum of over all the next actions. I mean, think that you have in a real case not only 4 alternative actions moving up, left, right, or down, but you may have diagonal moving and down also. It could be quite circular. There will be many pixels around your pixel. Okay? So what you're going to do is try to calculate all of them, see what the maximum value you get is based on that calculation on all next actions. Okay? Stop me if I'm not making sense or if you do not understand or if I say something wrong, which is quite possible. And that's the maximum over all actions of that parenthesis, which is the reward at this state, given that you take that action from that state. And the sum of all the other values that you have calculated in all the other actions in the neighboring cells, basically, times their probabilities of reaching that state or that value, because that value is related to a next state, another state, right? And the probability of reaching that is the probability of being in this state, taking the action that will bring you to that next state. And then you have this funny thing here, the gamma. It is a discount factor. That's called a discount factor. Because if you just had the probabilities and the values and the rewards, then this part is not the reward, sorry, but this part, which is the sum over all the next states, okay? That's premise next state, and the sum of all the next states has to be the effect of all the future moves. That has to be somehow reduced slightly, so that you do not only take decisions on some probable state in 10 moves, okay? That you have a higher emphasis on the reward now from this state taking that action. So this is an adjustment factor. And this is one of the things that's very nice when you see this kind of formula. It's very, when you're playing around with these and seeing how much it learns and how much it works, it's very simple. You don't do much with anything. You just change the reward values, for example, a little bit, increase reward in certain cells and maybe all cells, or decrease that. And you change the gamma value a little bit, and you will see immediately that the behavior will be changed. Okay? So that is the Bellman equation. Yes?
Oh, yeah, that was good. But I was just wondering, we don't know the penalty unless we take the step, right? Or we're just discovering the penalties while we are discovering the path, right? Oh, no.
Yes. You do not, well, you can assume penalties, approximately.
I just don't entirely understand why we need to introduce probability. So, unless probability of taking the step, why do we need that?
Because it's not equal as you learn, there will be change, but those will be changing. They're not always the same. But it is true, we don't know anything, or the fighter plane doesn't know anything initially. It has to go around. That's why it is learning. It's reinforcement learning. So as you do wrong stuff, you're getting punished. As you do right stuff, you're getting rewards, and you're registering a little book. You're registering all those outcomes, and those outcomes are related to this formula, basically. Okay? This probably you're not learning. You could. I haven't seen any algorithm doing that, but I'm not the best in this kind of environment. But you can actually play with rewards, and you will be able to repopulate the problem. And we'll see that in the next step when we start using neural network. It's going to be more or less the same. We won't know anything until we go around and experiment, experience, explore, as I said. Those three words I use. You have to explore, learn. It's too bad for the first 3 fighter jets that go up there. But that's life. You have to learn. That's learn.
But basically what you're saying is that you're learning the probabilities. So those are the sort of unknowns that you can find. The ones that maximize your expected payoff.
Well, yeah, more or less. In a sense, yes. Because the rewards you can have more or less constant. But you will see that actually, this actually is not what we are using today. You will see that we will turn them into Q values, basically, which is a combination of, and which takes into account time difference, because there is, as your question actually implies, there is as you learn, your landscape and your behavior with respect to your landscape changes. So one run, the result of one run isn't the same as the result of the second run. So there's always a stochastic element, something happening, and things changing in your learning that will change. So you will have to take into account what we call the temporal difference between each step of learning as well. We'll see that. I'm trying to, yeah, this is more or less the same thing we said. See, this is the kind of, this is just experiment, nothing else, no probabilities, no gamma, no nothing. It's just the rewards we're looking at, just setting the rewards and what can happen when you have very high rewards or very low rewards. Penalties in this case because they're all minus. You see, if you have no reward of any kind, it will sort of, and this is code by the way, so you can actually experiment with it and see what it's doing. It will just go around more or less randomly, hit a wall or jump into the -1, which would be the Death Star or fire or whatever your biggest penalty is. It will just go around, basically, okay? But the moment you change the penalty, saying, okay, you can't just go around, you have to find the goal. You have to find your end goal. You change the reward here, okay? Which then changes as compared to that, as you see that guy is hitting his head. This suddenly has changed. That will then give him too much penalty over time, accumulated penalty, so it will change its behavior to try to go closer to the +1, the reward. Okay? And the same here, this was sort of funny, no reason why it should be trying to go down, and that has also changed. And if you change again the reward, you see just a little bit more penalty. The reward is the increasing value is actually a penalty because it's minus, right? So if you just increase it a little bit more, it will also then stop doing these things once it's come here. It would have been more logical to find an optimal path up, right? So that's what it's trying to do now. Okay? And for the fun of it, you can do things like this. You can, just to make life a little bit more fun and harder for the fighter, you set the penalty to, or the reward to -2. What do you think happens? Well, this reward is +1. This penalty is -1. That is much higher than any one of them. Okay? When you hit the goal, you get +1. When you fall into the Death Star, you get -1. Well, but your reward in your equation is -2. And what does it do? It says, okay, this is too high. I'll jump into this. That's what happens, basically. It's much higher. So you have to be, you have to realize and have correct levels of reward that do not necessarily exceed the real penalties out there and the real rewards. Okay? Otherwise, we're going to have suicidal machine intelligence. I don't know what it's called. Anyway. Yeah, that was the suicidal stuff. Okay, that was the Bellman equation, basically. But now we're going to go over to Q-learning. There are several different ways of doing learning, doing reinforcement learning. Reinforcement learning is just teaching an intelligence using rewards basically, and properties of rolling that out if you can, if you have that kind of code that's implemented. Because not all of them actually do go back and change the properties. It can be preset as well. Then you have to know the board playing board. Okay? There are the static and the dynamic ones of reinforcement learning. And the Bellman equation that we just looked at is the static one. It is in many ways pre-coded rules. It's like very little stochastic, very little room for random things changing around. And, yeah, that's okay? The dynamic database stochastic processes are slightly different. They're very related to Markov decision processes. I'm not going to say too much about that. But as I said, in the stochastic version, it's not just the rules, it's the value that you're calculating, the V of S, if you remember. That's based on your state and action and all those properties and rewards. That's not the same every time. So, in a sense, you have value at time t, and then you have value at time t plus 1, and then t plus 2, etc., etc. With changes, they are not the same. So what you do is you calculate the difference of those as well. So, and try to understand the stochastic nature of the landscape you're in. That's one of the things that we will be seeing, which is called temporal difference. And we have, these have their own terms. When you create a Bellman equation for reinforcement learning, that is called a plan. But when you create a stochastic version of that, it's called a policy, because it's no longer a real rule. It can't be a plan. It just is a guideline to what the thing should be doing and how it should be learning. Yeah, came back. Good, good. I moved. We're now going to introduce stochasticity, and the moment we introduce stochasticity, then we do not have the V but the Q. It replaces the V, the value. Basically, it's called now Q-learning. We're going to look at the actual value of the action itself. What is the value of taking this action? That's what we're looking at. And that's more or less the same as you see. That's still an expected value. But what we do is we, in a sense, add the maximum of all the possible actions that can be taken from the next stage. So we had this maximum early on the other side. This has sort of changed. Okay? And we emphasize this is a very tiny, looks like a tiny change. What we've done is we've emphasized the value of the action, basically, of all the actions that can be. The value is no longer really calculated. It's most of the one. The other one is also sort of going around and learning, but it is more static. Things that change, not really. This one needs training. And as I said, this what we're looking at is the temporal difference. Because of the introduced stochasticity, we have the value now at time t and the value at time t plus 1 and all that stuff. And we take the difference and base ourselves on why would we take the difference? What does it give us? Think. We've gone and down, we've calculated the value, another round, 100 or 100,000 rounds, and we've calculated another set of values. And we take the difference. The goal, naturally, is to minimize. So that from one step to the next, you're not doing so many or as many mistakes as you did before, basically. Okay? That's what we'll be using now. That is the next cube, and this is the current cube. As I said, it doesn't say t and t plus 1, but think of it as time moving along. One of them is at t and the other is yeah, which is what we're looking at. Okay? So once you look at it in terms of previous step and comparison between previous step value and the now step, current step value, and this automatically, intuitively indicates how quickly you're learning, and whether you're learning, whether you're diverging, actually, not learning, diverging from the actual goal, whatever that is, or actually converging, learning more and more, doing better and better. That's the reason we have that. Okay. And sorry that I have to run so fast through this. This was what we did in one whole meetup last time, but it is we have more, so I have to summarize this. I know that there are probably many questions in your heads. If you want to ask them, ask now. Or if you have any comments, any corrections, any additions, come on. No? I'm sure it's not crystal clear, but we'll go on. I will just try to summarize again. What we've done is actually put rewards to taking different actions. First, just with probability, sometimes predefined, and in the other case, calculated as you go out, basically, and we looked at our learning process, whether it, in a sense, is in positive direction, which means that every time we go around and try something and reach the goal, we're doing it better as compared to the last time. One, that's a very, very rough summary. And those are based on a state and action, and the probability of action that you take from one to the other. And if you're going to be a good chess player, of course, not just the next action, but also the maximum of all the actions, the value of the maximum of the actions that you're going to be taking from this state into the next steps. Okay? That's the idea. The animals of the show, this is okay just to look at. I am going to be using Python 2.7, not 3, by the way, because I mean 3 is not very different from Python 2, and there is a problem with 3. It's relatively new, so most of the libraries and modules that we need are not ready for 3. That's the reason. That's the main reason we're using 2.7. Okay? It will be at one point. We're crossing our fingers, but it's been some time since 3 is introduced, because there is a lot of people who use 2, and the libraries of 2, the passage, the deprecation of Python 2 has not happened yet. It's probably going to take quite some time before that really happens. 2 has a lot of libraries. Another thing I already in a sense said, Python is just a programming language. It's a sweet little programming language. It does a lot of nice things, in an easy manner, but it's not a programming language per se. That's the thing. Like most other open source languages, with a community around them, the community and how they contribute, and all the libraries and modules that are available on it, is the real value in Python. So that's the reason why we can't move to Python 3, because all the libraries that we want to use are not really moved across yet. So we're going to be using Python as the Python icon, Python 2.7. I use a development environment called Anaconda, Python Anaconda. These are all big snakes, basically. And for some reason, there is an integrated development environment for Python in Anaconda. That's called Spider. That is what we will be running, the coding in, testing in, and running. Just to show what it looks like, maybe. No, a little bit. We'll be getting there, but it's okay. This is Anaconda, okay? And one of the nicest things with Anaconda that I use a lot is that I have shortcuts to Notebook, which is the coding and exploration environment that I have started to like, and that's what you have in this course. The code that I'm going to use and show here is in Jupyter Notebook, and Spider is the integrated development environment, but you have all kinds of other stuff. You have console, you have Microsoft VS Code integrated development environment as well. It's not really as effective as Spider. I use Spider, but it is also okay for relatively experimental, fast coding, some small projects, etc., etc. And you see that there is not only Python in Anaconda, but also R, which is the, in a sense, the competing language of statisticians, data scientists. It is a very rich language. It has the same, sort of the same history as Python. Someone needed a language specific for statistics and data science, and suddenly there was a big community around it, and people started contributing. So it has lots of libraries. That's the same. Well, that's what I usually use. Okay, this is, I'm not going to go through this, but I will show you a little bit of the logic. You've seen our nice little grid. You can actually create a grid and create an intelligent agent in the grid that goes around and tells you actually what it's doing, what values it has in each state, etc., etc. That is one of the examples that I used, which I'm not going to use this time. It's here you have the link, and all this stuff is, by the way, on the in GitHub, and the link to GitHub is on the page, the meetup page, so you can access all this stuff easily. It will be there for quite some time. It is actually a course in AI from Berkeley from some time ago, and the code is available, as well as the exercises and the homeworks for completing this. It's not complete code that I have out there. I didn't actually pull the code in. I just put a link to the code. Okay? The grid world itself has a lot of parameters that you can run it with. You can change the speed of animation. There is an animation, as you will see. And you can change the reward, as you see, that we make it higher, lower, etc., etc. And this, you remember the gamma, that was the discount for the sum of probabilities times states, which was the next states, which was the, which was the future steps, the probability total, the average probability of the future states, that you can discount, that you should discount, so that the reward part of the equation is not, in a sense, overtaken by the future rewards. Okay? So that's the kind of stuff that you can do. What does it look like? Let's see. Where are you? That's not right. That's not. My God. Okay. I have to stop the presentation because I can't see. Yes. I found my way. Okay, what you can do is, I don't think you see this at all, so let me see if I can do something like slightly better, right? A bit better? Right. The code, the entry file to the code is called gridwall.py, and you run Python file using the command Python if it's installed in your system. It should be if you're using a Mac. If not, if you're using PC, go to the Python site. It will tell you how to install it, and then it will be on the command. Instead of the terminal, the Unix terminal, the OS X terminal, you will have a command terminal in Microsoft Word, and you can do more or less the same things. Okay? You run just by giving the file name.py. Never forget the extension, because it does not assume the extension. The Python command does not assume the extension. Okay? And what it will do, you will have to be very careful, because it's going to go very fast, and I don't have time to do anything else. It will just go around, as you see, and give you the values, the what actions it took and what rewards. But the only reward that I have embedded in it, because I did not, this is not the one that is solved with all the examples around. It just goes around and finds, stops when it finds reward 1. All the other rewards, as you see, is 0, and then it stops. But it is, you will be able to do, if you do the exercises that I have a link to. Sorry, it's the contact. Did anything happen? This happened the last time as well. Alright. Okay, I'm not supposed to touch the computer because it doesn't behave. As I said. This is coming and going. It has its own volition. Yeah, now it's okay. Shall we take a 5-minute break? Because this is a natural break. I can just talk a little bit and then we take a break. What you've seen is basically that I will show you how it would look like when you have the rewards and all that stuff, the Q values. The grid will be filled in with those values if you do the exercises that is in that link, and that's a homework for you. And the code is actually the basic code is there, so you will understand, if you understood a little bit the formula that I've just gone through. The code is really there, and it is relatively one-to-one with the code, so you will be able to understand it relatively easily. Okay. But that was actually the summary of the last session, not the new one. So it is, in a sense, it's a good natural break. If you want to drink something or if there's any other pizza, take 5 minutes until we have this.
Jag provar. Tack så mycket.
And the homework, fun stuff we do not have time for. It's always like that. This is the, you have the link to, at the top, Berkeley, reinforcement of HDM. That is where you have the course. It has lots of very nice exercises, but this, that link is to reinforcement learning, basically. You will see that it has lots of exercises. And once you do the exercise, you will end up with, oops, we are working with VGA. You see there's a little bit more here. You don't see that. That's okay. You will see grid, your grid suddenly become aligned with these Q values, the worth of taking the step, the action to the next, okay? And you will see them as you learn in different directions as well and all that stuff. So it's, you just look at the exercise. It is a very nice exercise, and if you have questions related to how this works, both the standard Bellman equation, the reinforcement learning, regular non-stochastic version, and the stochastic version with changing temporal difference and changing probabilities, that is going to be a very good exercise. Okay? So we get to where we actually should be, the second part, where we have now not the grid animal, not the gaming Pac-Man version, but a tiny little car that will be learning. You will see at the very end, and I just sort of passed very fast. It says 150 crowns. This is, I have a mathematics background and a computer science background, but I actually learned a good deal of the neural network stuff from these guys. So a good deal of the code, or Berkeley or Stanford, because they are open. This one is not open, that's 150 crowns, but this is, believe me, one of the best. So you can do that, and I refer to it because I've taken a good deal from them. Okay? Not the Berkeley stuff, because the Berkeley stuff is from Berkeley, and that's open. Okay. Now the recommended tool set is slightly different. We have the animals, but now we have fruits as well, if you want to try out the code. And the two new things that we are going to be introducing is PyTorch and Kiwi. Kiwi, fun, not important for this case. Kiwi is the application framework, basically. It's the module that you borrow the app module from. It's the library that you borrow the app module from, creating an application simply. And it does things like help you create windows and other widgets and that, this and that, and do animations that we need. In the other one, in the previous example, in the Berkeley example, the equivalent library was not Kiwi, but tkinter, I-N-T-E-R. tkinter does not work with version 3 of Python. It only works with version 2. And one of my self-inflicted penalties these days is converting it to version 3. Actually, that's what I'm doing. I'm not very far from the result. So tkinter, just be aware, I'll probably post it on the page as well. I am trying to convert it so that it runs on 3.7 as well. Okay? It's a very good environment, but it doesn't exist for 3. And this one is new. Kiwi is much newer than tkinter. tkinter is, as always, me as variable. Okay? I mean it. It's not only for Python. It's from the Tcl family of tools, which is as old as Digital Equipment Corporation and Vax VMS. So, you know, if you know what I'm talking about, you know how old that is. All right. This one is the real one, and you see that I'm sort of talking with capitals here. Absolutely. One of the reasons is because if you do not understand tensor logic, you can still create neural networks, but it's going to take you a lifetime, slightly less, and it's going to be very painful, okay? It's like you can do everything with an array, right? You can do matrix arithmetic as well. But you don't do that. You import a library that does matrix arithmetic for you. This is about the same thing. You import a library that does tensor arithmetic for you. Once a tensor, well, it's a multi-dimensional matrix. It's not limited to 1 or 2 dimensions. It's many, many, many dimensions. And tensors are the kind of stuff, if you think of x, y, and z directions just in 3 dimensions, for example, we used to use them in physics for calculating force. So much force here, so much force here, so much force here. Where does it point to? Where is the push, actually? That kind of stuff is where the tensors come from. In this case, tensor is when we have the neural network with lots of things that are being connected to lots of things. It becomes a multidimensional array or vector, actually. So we need them. And the tensor, PyTorch tensor library comes with stuff that is tuned for neural networks. So we will be seeing things like weights that are the things that we changed, not the probabilities this time, basically. The weights are the learning parameters of a neural network, more or less. And things like if you want to apply certain functions for action selection, we will see again, that is also free. You don't have to implement that. So there are lots of things in neural networks that come free with a tensor library. PyTorch is not the only tensor library. The most common, the most popular one, the most used one is TensorFlow, if I am not mistaken. I'm going to take it with a pinch of salt. I don't know whether it's used, which one is used more, but TensorFlow is the one that you will usually hear about, not so much PyTorch. PyTorch is newer. TensorFlow is Google's tensor library. PyTorch is created by Facebook and NVIDIA in cooperation.
So one advantage of PyTorch is that it can run parallel GPUs and threads, okay? Because it is memory, so it can actually use the GPU, the graphical processing unit, much better than TensorFlow. It doesn't mean that Google is sitting and just twiddling thumbs. They are probably going to do the same thing eventually. But at this point, PyTorch is much more effective. All right? And you know the animals, Python, Spider, and Anaconda, that's the same development environment. The only difference is that we're going to be importing two libraries. And believe me, it's going to take some time. So if you are going to start, better make sure that you have a few, at least an hour for doing this, okay? Yeah, we can start to look at the journey. So, what is a neural network is where we start. A neural network is an imitation of the neural stuff in the gray matter that we have up in our heads, basically, which looks something like this. It has a neuron in the middle, and it has synapses, the dendrils that go out, the antenna, the tentacles, okay? And dendrites, the touching points, basically. They don't really touch each other. A neuron does not really touch another one. They are in an electrochemical solution, and they sort of communicate by putting signals into that solution and the other one receiving. But anyway, so we assume in our simulation that they touch, okay? And then there is the axon that gives an output with all kinds of, it would be as crowded as this, and matching the dendrils of the other one, basically, so that they sort of communicate. But the guy who actually computes, this is input. This is the computing center, and that is the output, basically. So what we do is sort of simulate that, all right? Lots of inputs, okay, so you have lots of inputs. That's the first step in a neural network. And then outputs, many or one, basically. And then you have a middle layer, and the middle layer is usually called the hidden layers, okay? And they exist in several versions, of course. This one is the dendrites. That is the neuron that is doing the job, basically, okay? And this is the axon, that's the output. But you can have different versions of them. You've seen this one with 3 inputs, in this case, not 1, 2, 3, 4, 5, but, and then a hidden layer with 4 nodes, whatever that is. You don't know what they're doing. You can actually these days look into them, but anyway, that's a hidden layer. And then there is an output layer. And what's important maybe here is that there are these weights here, okay? And there are certain probabilities, you don't see it in this diagram, certain probabilities that are attached to this. What happens is that the input goes in and with certain weights delivering some triggering information to the hidden layer, okay? And then the hidden layer shoot out some things to some of the output or all of them. It doesn't have to be all of them. It's shown as everything is connected to everything. In principle, yes, but it's not really true. Some of the stuff will die out, connection. Some of the stuff will be enhanced eventually the same year. These weights represent, in many ways, how important these are. It's almost like a classification weight of getting the inputs to the right neurons and saying the hidden layer neuron elements, saying these 2 are the more important for you and not the other ones. And the next one, okay, that one is not those 2, but another one is more important for you. Those weights. And the probabilities here in the output layer will show which result is the most likely. In our case, we will have 3 here. The 3 directions, either going straight or left or right, okay? We will have something like, I don't remember, we can look at in the code, but 10 or 20 pixels of movement in each direction, basically, and which direction we're going to choose, which is the most likely or the least bad, if you want, the other way around, direction that we are going to choose is in our case. But it can be anything else, okay? That's the output layer. At the end of the output layer, there's usually an action selection algorithm or function as well. Here you see, that is the shallow case. We have only one hidden layer. And then, as you see, we have shallow, deep, deeper, and the deep version is maybe with 2 or 3 layers, okay? And it's the same. Everything is initially connected to everything, and there is only one set of input, only one set of output. But the learning, the part that does the work of the neuron, and there are ways as well. By the way, it's not depicted, but there are. The learning happens in the hidden layer. Input is just input. The sensors, the 3 sensors of the car. Okay? If you remember, the car doesn't have 3 colored eyes. Those are the sensors. And then the output is the direction that it's going to go. And the hidden layer is the learning stuff. Okay? And of course, it can be even deeper. So it's sort of up to you. And one of the exercises you will see at the end, after we play a little bit with the code, I've left some things for you to do, some simple stuff. If you will see, if you understand the tensor logic, you will be able to create several hidden layers. And it's a bit up to you. You play around with how many nodes is the hidden layer going to have, or how many hidden layers you're going to have on each one, how many nodes, basically. So those are the things that you can play with. Okay. Here we are. This was the grid. This is a grid, just like the grid world grid that we have. And what you can do with the grid, you can also see the grid as numbered. Okay? You can think of this as one dimension, the rows and the columns, basically. And this is the first, what would that be? Column, first row, second column, first row, etc., etc. We start from here. That's why we start numbering from. It doesn't have to be like that, of course. And you see that it is in many ways a bidirectional graph. Okay? And don't be surprised if you see people talking about graphs or actually using graph techniques with analytical capabilities to implement this kind of stuff. So there is no surprise. It's a bidirectional graph. Bidirectional means that you can move from here, but you can also, by mistake, move back as well. So the path is open to move back and forward. All right? Okay, so once we know that this is sort of a graph and that we can actually number the grid cells, then it sort of starts making sense what we can maybe do by throwing a neural network at it, maybe extending the Q-learning stuff with a neural network and make a deep Q-learning algorithm. You have the states and the rewards at any point. Okay, you can number them. That's A and B axis, or the column and the row axis, whatever. You can number them. And you have in anything, any agent that you put in, this is one kind of agent. So it changes with the agent what the goal is and what the sensors are. This funny agent of ours has 3 sensors. Okay? These. Oops. These 3 sensors. One of them is left, right, and ahead. Is there anything in front of you, or a little bit on your left or right? Remember the sand dunes or the sand that we don't want to crash the car, so we sort of put sand instead when it is learning. I don't know whether they do that, by the way. Okay, so those are the input senses. That's really the density of the sand. If it's a lot of sand, then it will slow down much more and we'll get more penalty. That's the idea. And we added something here to that network of ours. The output can be several different, okay? And what would be in a car? Well, we want to go from, now let's see that there's no road, it's just an open landscape. That's how we will start. What are we going to do? Well, in our case, we've defined home and work at each end of the diagonal of one window, one screen, basically. So it will try to find both endpoints, the home and the work, and then it will try to go in between them without going crazy. Basically, it will try to find the path to them. So the actual output is not 2, it's not 3. The output layer that we have here will typically be the alternative actions that we can do. What could be the alternative actions? Turning towards the left, turning towards the right, and going straight, for example. Okay? And then, of course, updating your state and this and that, so it becomes a tensor with different elements, the output actually, and we have to choose one of the most likely, most certain output. So what we do that you don't see because I'm using VGA, maybe we could push, anybody tall enough? You knew that I would be coming to you. Can you just push that thing a little bit to the left because it is the reason.
Maybe we can.
Huh? Nobody is willing to do that?
I don't think it's the projector, because if you look at the wall behind the
Maybe
speaker,
it's.
no.
Maybe. Anyway, sorry guys, this is the technology we have today. Sorry?
Maybe you can zoom out of the screen.
Can I?
I don't know.
Well, it's worth trying. I can't zoom out. Wait, I can do this though. I can zoom in and out in this mode. Let me see. Yeah, I got the whole thing inside. Well, anyway, then I can't use this, but it doesn't really matter. Now you see the whole thing, basically. So you see that I have the alternative outputs with some certainties, probabilities, possibilities, whatever you want to call them, okay, of which one is the best alternative output. That goes through an action selection function in the end. Kristen, forget it. We'll live about what we have, okay? We have an action selection function. There are many different action selection functions. We are going to be using, that's the reason I wrote softmax. It's one of the most used ones. We're going to use a function, a tiny little algorithm, that picks the best action, but there's a trick to this. The best action is not always the one that comes with the highest probability. You will see later on that we have a challenge in learning. We can optimize for a local reality, thinking that that's the absolute reality, and that's usually not the case. Well, not always the case, anyway. So what you want to do is choose the most likely, the most certain, most of the time, but not all the time. So that you, in a sense, willingly force the agent to experiment, to explore more. Until, to the point, where these alternative probabilities for the alternative actions become tinier and tinier and tinier and tinier, so that the likelihood of you taking one of the crazy actions becomes less, but then, by that time, you explore the whole landscape, okay? So that you do not focus on a local area and think that that's the reality. How can that be? I mean, imagine you're driving the car in a road like this, okay? The car is driving, nicely. Nothing is changing. What's happening to those parameters? the guy is becoming more certain because nothing is really changing. Ah, I'm learning. Nah, that's good. But then there's a swing there, and then his life becomes miserable. So I didn't foresee that. Okay? So that kind of local reality and changes in the reality, in the landscape, has to be managed so that the car doesn't just go all the way to the other end, bump his head, and then has to come back. Okay? So that it can actually learn to take the swing. Nice. Right? That's the kind of stuff that we're talking about. And we have other techniques as well that we have to, or challenges and related techniques as well that we need. Maybe, yeah, that was exactly what I said. We have this very important principle in learning machinery, usually. If it is too monotonous, your environment, if it is too good to be true, then it probably is not true, more or less. So you have to make sure, and never to forget, also when coding, that you open up for alternative learning experiences, exploring the stuff. So in the code, what we do is, this is what I said, we don't want that bias to be reflected in our learning algorithm. So what we do is we store, it's going around and it's doing experience. Every step is an experience, okay? It does this several times, maybe it goes around and around, there's another round and another. That's very good. We store that in what we call experience replay memory in the code. You will see that it is the actual code, it's called experience replay, okay? And what we do is we choose a batch from experience replay. That may be, that memory may be 100,000 elements. This is exactly what the code, we have set it up in the code. But you may want to just pick 1,000 of them, or maybe 5,000 of them, okay? So that you don't have the whole 100,000 all the time, but you pick a limited amount randomly and use that as your experience the next time. And that's called breaking habits, okay? That would be very nice if we could, as humans, do as well, but I have problems with habits. I don't know about you. I could maybe randomly do other things that I usually do. Anyway. What we have here, the learning, actual learning, is when I explain, you have input, a hidden layer that does things, and then the weights that says that this input is more important to this, that and that input is more important to these, etc., etc. And then the weights, that's what manages the inputs, not the inputs, but the inputs the translation to the hidden layer, basically. Okay? And then we have the probabilities here of potential outcomes, and then we have this action selection. Once the action is selected, what did we do? Think of reinforcement learning now. We've taken an action, and it's going to have a penalty or a reward now. Okay? And that we need to feed back into the system, otherwise there won't be any learning. So how do we feed back? What is it that we feed it back to, basically? Well, we take the action and the target, the sort of cost of doing mistakes, we try to calculate, okay? And then we see which silly guys here are these weights is how much responsible for that error, okay? That's exactly what we do. So we update the weights by looking at how much of the error each weight is responsible for. Because they have weights, they have different contributions to the error made. Okay? That's what we call the backward propagation. Okay. In these kinds of stuff, I've talked about local realities. And this is very typical when you're looking at backward propagation and all that stuff. And in most of the other calculations, what you're doing is going through and trying to find in an environment which is, imagine, a really heavy neural network with maybe 100 input, more than 100 times 3, 4, 5 hidden layers maybe. How realistic that is, I don't know. It depends. Most of the stuff can be done with simplest neural networks, but some of the neural networks will be many nodes, many layers, and each one connected to each other. Can you imagine how many passes and tests that would imply? Well, some guy has calculated, if you take this course in Udemy, I don't remember exactly what it was, but they had one example of finding a minimum, or maximum for that matter, which would take about the time it took the world to develop from its birth and or the human beings to exist, or I don't remember, but millions, billions of years on the fastest computer in the world, which I don't remember how many peta or whatever flops. Do you know which machine is the fastest in the world? It's a Chinese machine. Are you afraid of the Chinese guys? Okay, but that machine, even that machine can't do it in a lifetime. Not in 10 lifetimes either. So we have to be very intelligent when we use algorithms that try to compare many things and find a minimum or a maximum. One of the algorithms that we are using is called gradient descent. It's simple. Think of this curve as many tiny points. If you wanted to go a step, and you're the ball that's rolling down, okay? You take a step, stop, and test whether either you came to the minimum or not, and you have to take the next step and probably a step back as well to be able to compare. That's the way the brute force algorithms usually work, okay? That's the one that will take a lifetime or more, okay? Many like that. So what you do instead is look at the gradient, the tangent, at the point of the wall going down, and look at the direction of it. And then you jump as far as you can initially. For example, okay? And you look at the gradient, and the gradient doesn't only change direction, but it also changes slope. The value of the gradient changes. So you can actually intelligently guess how far you have to jump, and more or less where a local minimum is. In much fewer steps, fully possible within the lifetime of a human being, actually much less time than taking a cup of coffee, even less time than taking a sip from a cup of coffee. It is very fast, these algorithms, okay? But there's a slight problem, the same as I mentioned earlier. You may end up in a local minimum, or a local maximum, whatever it is that you're looking for, and not find the actual truth, the actual minimum. So that is one of the reasons we use this huge memory and batches randomly selected, maybe using a uniform random distribution or sorts, so that you do not get stuck here and you sort of jump around in the decision spaces. You can think of the actual space as well, but this is the decision space when you're looking for whatever the maximum or minimum you're looking for, basically. That's called gradient descent, and that would be part of our tensor set as well. Yeah, let's see. Now that you have the basics, what's the basics? You have inputs, you have a hidden layer, or maybe more, and you have outputs, and the outputs will have probabilities or certainties is what people usually call them. In the case of the car, you will see the certainty in the way it behaves. It behaves like a drunkard if it's not certain, because what it will do is it will more often than not choose, drop the best or certain alternative and go for something else. And then it will go like that. Very bad habit to develop, okay? So let's go and look at the code. This is, let me see. Yeah, actually. Can you see this, or shall I just make it just a little bit bigger? Is it okay to see, more or less? I'm actually asking the guys at the very back to see. I know that you can see. Anyway, this is in the GitHub repository that I have shared on the meetup page. You can find it. It is a Jupyter notebook, and it explains the code, etc., etc. So this is just all the stuff. First part of the, well, I have to say something before we go into the code. There are two Python files, okay? One of them is called map.py. That's also the same in the Udemy course, so you will be able to look and compare it. Except that there's some changes here, and the major change is that it is heavily commented so that you can see it, okay? And then there is the AI.py. The map.py is the one that creates the map that we're going to drive around in. It's a window. And it gives us the possibility of drawing some sand dunes or roads on it. And the AI.py, AI Python module, is the one that implements the deep Q learning network, the neural network, initiates and updates, basically, okay? So we're going to be not going to be looking at the map.py because, well, it is here as well, by the way, and it is commented, you can read it yourself, but I am not going to explain much of it in this course because we're going to try to look at how you implement the intelligence, not the application, okay? The first thing when you start looking at the AI.py module is that there are a number of libraries that are included. As I mentioned, Python is a nice language. I like it more and more as I get more experienced in it. That happens with any language, actually. But the real strength of Python is, or those kinds of popular programming languages, is their libraries, what other people have developed, so that you can actually not have to redevelop every single thing, a window, a tiny little car, or a TensorFlow neural network. Those things are the more important things. So watch out. And I have a link here, the 20 Python libraries you can't live without. It doesn't include the tensor libraries, but it is all the other typical libraries that you would be using. Just take a look at that, okay? I'm not going to dwell on the other stuff, but as you see, we have a library called NumPy. It is the library that you will see in almost every single Python code at the beginning, one of the first. One of the reasons is because it is the scientific arithmetical library, especially if it's sort of scientific computing, data science kind of stuff, and that's going to be included. So one nice thing with NumPy is that it can do most of the things most other libraries can do, but it is sort of slightly heavier to do. It can also do vectors, linear algebra. But the problem is that it doesn't do it as well as a module that is specific for linear algebra. You can also create tensors using it, but it won't be as efficient. So we have libraries specific for linear algebra and for tensors, okay? The other one that you will use a lot is OS, operating system, okay? And that's for doing operating system kind of stuff, getting the date and opening a file, closing a file, writing into a file, that kind of stuff, okay? Random is a library that we use, that we are using here, for randomizing. And what are we randomizing? I just told you, guys. We have to randomly select a batch out of our experience memory. That is what we're going to use random for. Okay? And then we are going to be using Torch or PyTorch. Torch is the older version. PyTorch is the new version that includes Torch, mostly. Torch is our tensor library, and we're going to use it for creating, basically, we'll see in the code, the number of inputs and outputs and all that stuff, and connecting them to each other, and then being able to connect weights and whatever to all the connections, plus for finding useful functions for doing different things, like the softmax function that we just looked at, okay? And here is something that explains what PyTorch is and why it is so interesting. It's talking about CUDA, as Compute Unified Device Architecture, that is created by NVIDIA and helps Torch run much more efficiently on GPU, graphic processing unit. Okay? We have, let me see what else we are using. Within the Torch library, we are using modules like the NN module. You could guess what it stands for, neural network. That's for creating the neural network, the actual neural network. So you see that just taking Torch gives you the chance to just declare a neural network instead of implementing it yourself, basically, okay? And then we'll use something called functional, which is the kind of module within Torch itself, the library itself, that helps us define functions like gradient descent, like softmax, kind of stuff, okay? Yeah, and one of the nice, we're going to use AutoGrad for doing mappings from variables to tensors and back and forth, okay? The import section then looks like this. This is very typical, that's NumPy. As NP, for those who know Python, it's not a problem. But instead of having to use the longer names, we sort of shortcut them. That's an abbreviation. Okay, this is short enough, we don't need that, and those are not very often used in themselves. But we do this, for example, in the Torch.nn, that was the neural network sublibrary, the module in the library. We abbreviated as NN, and the functional, which gives us all the nice softmax and gradient descent-like functions, as capital F. And there is an optimization function. We abbreviate as Optim. And then in the 2 steps, the AutoGrad, that is, we're going to use the variable, this mapping from standard variables to tensors and back. That we're going to use called variable, basically. Okay? Good. In practically, this is the explanation of the network class. That's after the, by the way, if you go into this and pick the code parts of this and put it into a file, it will become a fully runnable AI.py. Do that. Okay? All classes start with an init function. That's the mandatory first function. Because a class is a template for generating objects, instances, and every time you instantiate an object, you need to do some initializations, typically, okay? And that is the init function that we use that for. We will initiate the function to create the bare bones neural network, basically. And we will create a shallow one with only one. And one of the exercises, just to add another one, there's an example here that helps you see how you can do that. Okay? There are some tutorials that I am pointing to that you should go and look. One of the nicest things, I mean, remember this capitalized absolutely, you have to read Deutsch, PyTorch. The tensor logic, if you don't understand it, it's difficult to understand exactly what this is doing. You may think you understood it, but this is computer, this is code. You need to understand exactly what's happening with which parameters and all that stuff. So one of the things that you can do is just go and do blitz, 60 minutes blitz of neural networks tutorials using PyTorch. It's a very interesting, nice little, really even less than 60 minutes. And it gives you the basic idea of most of the stuff that we're using here, okay? The forward function is the next function after the init function that we have in this class, the network class. Okay? The forward function will perform the forward flow. You remember that you have the forward flow with all the inputs passing through weights and the neural hidden layer, and then outputs, and then the action selection at the very end. That's the forward movement. And then the backward movement is taking the action that's selected and calculating the cost, the loss, with respect to what it should have been, and then reflecting it on the weights. Okay. As I said when I was talking about neurons, there is the actual neuron just shoots out signals, okay? It has something like, if you put so much level of voltage or electrical impulse into the neuron, if the sum is so much from all the dendrils and everything, then it will shoot out through the axon and into the others, into the other neurons, basically, okay? It's as if something is just triggering some level of a signal in the brain. And this is more or less what we do. We have in these hidden layers, and many other places as well, we can use these triggering functions so that if the input 1 and 3 goes to the hidden layer node 1 with weight 0.2 and 0.8, for example, at one point, it will be enough, if both signals exist, it will be enough to trigger some output, okay? So we have this, what we call the activation function. The activation function is the triggering function, basically. Depending on the input level or the sum of it, it does something. Okay? There are many activation functions. It can actually be a square function. That's 1 or 0, basically. It is nothing, 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 and then some signal. That could be one of them. Or it could be a curve, like this, or like this, depending on what we're trying to teach the neural network. The one that we are using could be something like this, for example. The one that we are using is this blue one. That's called the rectifier function. And the reason we are using that is because it's better than 0 or 1. It gives a level. It's not just either or. Okay? It gives a level. And the level can be used to reflect the certainty related to the output. Okay? So that we do not have this is the output or no output, but we have different outputs with different levels. And again, it would be an idea to have something that adds up to 1, like 0.1 for one and 0.2 for the other and 0.7 for the other. Okay? That kind of stuff. But that differentiation, for getting that differentiation, we need either something like this or something like this. This is the soft plus function. This is the rectifier function. We are going to be using the rectifier function. And where will that function be? Are we going to implement it Are you crazy? We've used all our time to learn PyTorch and the functional module in PyTorch, which has all these functions in it, okay? Yeah. So this is what it looks like. I have already described what it is. I'm just going to go through it. One thing that you should be aware of is this little self. Self is when you have a class that instantiates an object, self points to the instantiated object that's calling these functions, the member functions. So practically anything that relates that is to be run, not by the whole class, but by the object, the instance that's created, needs to refer to self, okay? Yeah. What we're doing here is, because we have the network module, we just use the mother network. This is inheritance, and use its initiated first. And then we put things like input size, and input size is how many inputs, 1, 2, 3, our case 3 probably. It's actually 5, but we'll come to that. And then the number of actions we're going to use. And what we do here, this is where you create the neural network, okay? We take fully connected layer 1 from input to the hidden layer. And how many connections are there? There are input size many inputs, and we've somehow decided that there are going to be 30 nodes in the hidden layer. So we set up using the linear function of the NN neural network module that we imported, remember, and abbreviated with NN. Okay? We just say connect this many inputs to 30. And the second fully connected layer is again the same function, now from the hidden layer 30 to the output number of output. So if you wanted to have 2 hidden layers, what would you do? Was this a serious question? Not at this time of the day, so I'll answer it. You would probably have another, you would have from 30 to 50, maybe it's 50 nodes, the second hidden layer, and then from 50 to output. That's all. You would actually have one more like this, self.fc3, or this would change and fc3 would be this, basically. So there you have the right connection. When you put those connections in place, your neural network is almost okay. The important libraries make sure that it comes, it gets created, and with some very nice benefits. Some functions, member functions, that are specific for neural networks, like being able to calculate weights and this and that. That is part of it, okay? And then, of course, you have the forward that I'm explaining. I can't use so much time on each one of them. So this is the experience replay. That first one, if you remember, was the network class. And that starts with class network, all right? And this one is the replay memory, if you remember. That's the huge memory that the experience exploration memory, and the functions inside are the initialization with a certain capacity, and we are making sure that it does not exceed that capacity. We don't like things. Remember that these are sort of arrays and lists. So if you try to, if it has allocated just on the border of something important, you don't really want to exceed that memory that you have allocated. So what you do is you have a capacity, and then you create memory, which is a list, basically. See, memory, first an empty list. And then you create an append to memory or push function that pushes into the memory whatever event is to be pushed into that memory. The event is the experience, each experience basically, okay? And it tests for whether that exceeds capacity. If it does exceed capacity, if we have 1,000 memories, we thought of 1,000 long memory, and if it's the 1,001st one that we're going to append, then what you do is you delete the oldest. What is the oldest? Well, this is like most Unix world languages. The index 0 is the first element, which is the oldest because it's the first one we push. So what we do is we add one and then delete the one at index 0. And then this is the sample that we have. We take a sample of the memory, and the size of the sample we take is batch size. And there's something very funny here. Zip, star random sample. Okay. Random making, yes, it's a function. It chooses randomly a sample. That's what it is. But what is zip? All right. Don't despair. I think I have it here. What we have is, in our world of tenses, these kinds of vectors within vectors, maybe in many other directions and so forth. This is just an example, okay? This is something like a list with lists inside it that is a state, an action, and a reward. Just as an example, okay? And another state, next state, another action, another reward. That's the batch that we have when we pull it out from the memory, because that's how we pushed it in. Okay? But that doesn't really fit the tensor world that we're going to be living in, because we want all the states in one place, all the actions and all the rewards in one place. So what the zip function does is actually goes and picks the first of each element in the list and creates a tuple of those, and then goes picks the second element and creates another tuple, etc. So you end up with all the states at index 0, all the actions at index 1, and all the rewards at index 2, or whatever else. It's not exactly like that, but you should remember state and action, that's true, and we will not, in the code, we will often refer to this kind of list with index 0, then we are looking at the states. If we refer to it with index 1, then we're looking at the actions. Okay, now that you know what zip does. You see, that's the problem with libraries like PyTorch. They do a lot, but they are not easy to read when you first see them. Okay? Okay. Now we come to the Haley part. Dun, 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 DQ learning. The DQM class, DQ network class. We have 6 number functions, yes, I think so. No, 7 it should be. It says 6 here, but that's wrong. Okay, that should be 7. The first 4 will be starting with the mandatory init function, and then the select action. We have to be selecting the action at the end, remember? And the learn function, which is the select action is the forward movement. The learn function is feeding back, the backwards movement, okay? And the update function, because now that we've stepped into the next cell, we have to update the current state and action and all that stuff, so that our world starts with a new first step, basically, okay? And then we have the score function, fun, for computing the mean of all the rewards. There's a very simple reason, you will see. We want to actually see how this thing functions, how long it's going around with how many rewards, on a scale of rewards and time. You want to see the punishment reward curve. That's sort of stabilizing at one point, okay? So we want to be able to watch what it's doing when it meets barriers, what it slows down and all that stuff. Or when it goes berserk, because in the beginning of coding, everything goes berserk. You have to be able to see what happens, all right? The learn function is the one that is the key, and it would be okay to look at it. It says here, can you read this? So I will just go through this. I'm not doing most of them because it is very difficult to explain the code here and then go and look at the code. So I have, for this class and the rest, I have the comments in the code, mostly. But let's just look, because the learn function is very important. That is for training the deep learning network. It does the forward, and then it actually does a bit of the backward, but not fully. The aim is to get an output, compare it to the target. Well, it does the backward, sorry. The learn does. The selection, action selection does the forward. Sorry, I jumped because that's the function before. I thought we were there eventually, but no. I'm not explaining every single function in the same order, just this one. And that is the backwards propagation. It calculates the difference between the target and the actual output, okay? And then calculates a cost. What is the target? Who defines the target? This is like the probability question you're asking. So you answer that one. You know? Yes?
Sorry, was that a question or a statement?
Well, we're talking about a cost. That's the difference between the target and the output, actual output. Wow, the
I
whole.
think the target was defined before, right? I mean,
You have to define the target yourself. There is a target. And what's our target? Home. Home. We're going, the car is trying in this implementation,
but
okay?
the home has always been there, right? It's not like we defined it. I mean,
Yeah, we define it
So it's
when we
stated.
call the intelligence. We define a target for it, and we define punishment for running into the sand while not going to the, not going properly home, basically. So the target is also, in a sense, accumulated in the experience, the replay memory, basically. All right? So it's the previous best case against the actual, and the ultimate target is home. Or, I mean, in this case, I have defined it in the code. The target is work and home. That's the two diagonals of the screen that we're going to see. All right. So it's a cost function like we talked about. And then we're going to reflect onto the weights, adjust the weights according to the contribution each weight had on this error, as I mentioned. It is very well commented. You remember the gamma parameter? That's the gamma parameter. We are going to have a reward window, a sliding window, so that we can sort of, when we see it in a graph form, we don't see the whole thing. It becomes a bit difficult to see. So we create a sliding window of 100 events with rewards and all that stuff. And we create the memory for 100,000 transitions or events that we are going to store, experiences that we're going to store, all of them, basically. But then we're going to choose only about 1,000 of them, I think, if I remember correctly. When we choose this randomly, this batch every time, okay? LR is the learning rate. The learning, remember the temporal difference, the learning rate? That reflects the learning. We have something like this. It's related to the cost, okay? Are we getting closer every time? The cost is getting smaller and smaller, or larger and larger. I mean, we may be diverging, so we have to make sure, okay? Our state actually is more than just the three sensors. We have the orientation of the car and the mirror image of that, you see afterwards, etc., etc. The next function is select action, the selecting the right action. And as I mentioned, we're going to use softmax. And you see here a little explanation of a tiny little, where is it? There is a temperature, I will show it soon. We're sort of not just taking the action, but the probabilities, and then choosing the action from those probabilities. But we are, in a sense, sharpening those probabilities a little bit by multiplying it with something called a temperature. So that if the probabilities are 0.04 and 0.1185, what we want to do is, by manipulating this parameter, make the car more certain, or the decision more certain, in a sense. So what we do is, we use the softmax function, but multiply the three elements of the softmax. This is just the indexes of them. Multiply it by 3, and then what happens is, this one, it's a temperature function. It's not just multiplying. It's a very special multiplication. It, in a sense, makes the small smaller and the large larger. Okay? It sort of puts it on a curve where the smaller becomes smaller. Okay? So you will end up with 0 and 0.2 and 0.02 it should be, and 0.98. So one action becomes more dominant in that case. Okay? This is the line of code we have, and in the code you will see that it is multiplied by 0. And in the exercise we're going to do it with 0. What this does is actually stops learning. When you put 0 into the temperatures, then what it does is it does not pick an action properly. That's the max. So it doesn't learn. It never learns. And you will see, we'll try that. So, okay? Okay, and then there is this one that is not going to be, yeah, this one is okay, and yeah, we're going to be returning the action. And then there's the learn, I've just talked about it. It is actually gamma times next outputs plus the batch reward. Okay? It is the reward that we calculate from the batch that we've selected. It's not just one state we're operating with. We're operating with maybe 1,000 states, events, experiences, randomly selected. And then there is the update that I also talked about. And to be able to understand this conversion function, which is this here, with something called squeeze and unsqueeze, it is again mapping from a kind of variable to tensor and back. Okay. Not going to use too much time on it, but I said it already. To be able to understand the details of it, it's a very simple thing actually. It just turns around the vectors or recalculates so that it maps into a variable, basically. But look at it. Be sure that you understand it. And then there's the score function and the load function, which will score, load, and store functions. Score will do what I mentioned. It will actually take the means and draw a graph. And the load and store, just do that. It's the whole code is here, and you can do that. The next level is commented. I'm not going to go through it. Is the map py. You can just use it, but it is commented in the code, and you will be able to understand it. And you will see that we are calling the class DQM, instantiating and putting it into an object, an instance of the DQM class called the brain. That is the DQ network brain. And when we are instantiating it, see that we're instantiating it with 5 states and 5 inputs, etc., etc. 5 senses and 3 actions, and the gamma being 0.9. All right. This is pure application. That is the car widget, which is an ugly one. And yeah, and this is the game widget, which sort of makes it run around and all that. All right, that's the stuff we have. Let's see if it works. When you are going to start experimenting with this, there's one thing. It is already at the very end of the, hold on, I just do that. So you see, here. At the very end of this, there is, let's us play around a bit. Preamble, extract the code into two files, AIPY and MapPy first. Make sure that you are running MapPy, which will be using AIPI, because map is the application itself, and it just uses our neural network. Make sure that you go to the file explorer. You see variable explorer, file explorer help part here, and then click on this and restart kernel. That's very important for you to do, mainly because then when you go to that catalog, then it will assume that everything is in that catalog. Put everything in that catalog, okay? Then it will be having a good deal of fun. And of course, it will not start now. People, there is a problem in this. I have to stop. It will stop now. I will restart. That's explained here. And then run the fun. What are we going to do? We have made it. It's in the application code. Home is where the heart is, upper left corner. Okay. Okay. It is actually the upper left corner. And work is where the money gets accumulated. It's downstream. To lower right corner. It sort of gets boring when you look at the same code for several days. I commented, sorry. That's what happened. And this is the part where I have the temperature that you can play around with. You start with a 0 temperature in the select action member function of the mind, the brain, okay? And it says restart the kernel before you try again. It's it will have I can't explain it really. It shouldn't do that. It's in my mind, but I read it. I googled it up, and it seems it's almost like a planned function of SPI. It doesn't do well once you waited for a while, and once you made a mistake or anything happens to you, are thrown out. Let's see if it starts now. So that is one of the things that you're going to do. Another thing, don't update it if you're going to use Anaconda. Okay? Don't update your Anaconda. We're not done with the code, so I'm going to make this part. And I'm going to do exactly what I said. File Explorer. Where am I? Where are my documents? Where's my code? This is the code. And this is the one. Yeah. And then I do restart kernel so that it remembers that directory.
Yeah, I have a question regarding the actions that are coming out. So I think one of the actions was to move left, and one to move right, and one going forward.
Actually, it is 20 pixel direction change, yes,
Okay.
but it is sort of, yeah. To go straight or not.
Instead of using the rectifier activation function, couldn't you have used just a sigmoid and then define -1 as moving left and +1 to move right?
Yeah, yes. The answer is yes. I think it would even give a slightly better result, but I haven't experimented with it. Sigmoid function is a bit different. It's a smooth function like this, and it is explained in some way. Not here. Sorry, I didn't include it, I think, in my explanation, but
Not a sigmoid, but a tonnage in this case, because sigmoid will stop at 0.5. And you want it to be -1 to 1.
yeah. Well, you can always translate the sigmoid
Yeah,
as
of
well.
course.
It is the same kind of function. But yes, you could. The short answer is yes. I didn't because the original code doesn't, basically. And I did experiment with different ones. And those kinds of functions that span a larger area between 1 and -1 are more natural, in a sense. It does give a better result. It is one of the homeworks to improve. So yes, you can. And it is very easy, and it may sound like a very difficult homework, but the functional library, the module, it has all these functions that we're talking about. And you can actually look at Google activation functions, and you will get a list of them and where they are better and where they are not. But it's a very good comment, and it is correct. It actually will give a better result. I didn't really experiment so much with it, but I did try it. Sigmoid only. All right. So what you do is you select all the code and you run and hope that it will work. The stupid code. Did you see what it did? But look, it is learning.
What is it trying to optimize?
It is trying to find the way. It's not really optimizing. It's just trying to find a path from home to work and back. And in a sense, I do not have an optimizer here. Not really. I mean, if you put barriers, it will not find the shortest path. In that sense, it doesn't optimize. But in this case, it does. It sort of learns that the path is okay from there to there. See? But do you see how it's behaving? And if you read my funny midnight comments in the code itself, you will see that this will definitely be stopped by the police and made to blow his driving. So one of the things that we can actually do is, now it's learned a little bit. So what we can do is say save. And when you say save, this is what you can see as well. Let me see. Okay? This is what we did in the score function, if you remember, the mean of the rewards. It's taking in a moving window, basically. This is what it's doing. You see very clearly that at the beginning, when it sort of went around its own tail, that's where it started. It thought it was doing well. When it started to go around its own tail, it didn't find the goal. So it gave itself a real big beating, and then it started to come up, and now it's sort of stable. It's going from home, left, upper left, to down. It's not doing anything else. But of course, we're not going to make life so easy for him. You already saved the brain, so I'm going to just stop this silliness. All right, and then we go to AIPY. Where is the action selection? Oops, sorry. This is the select action one, and you see that we have these many. This many here. Is it saved? By the way? Yeah. So it should, if we increase it to, let's say 300. Temperature is 300, same. And then, correct? Of course not. It would have to, I forgot what I told you guys. Restart the camera. Ah, it's doing silly things. Okay, load, don't guy. What we did is actually load the intelligence, the weights that we had saved. So it's doing better. And you see that it is not doing this funny stuff. It's not, what it's not doing is actually choosing an alternative action, looking on the left and right more often. It's going like this, okay? So just by increasing the temperature, what we did was decrease the answer in the uncertain actions and increase the more certain action, make it more certain in itself. Okay, so that's what it's doing. And one of the things that you could also do is, let's save this again, and let's look at stuff here. Again, it was probably somewhere around here I remember that it had learned, because what does it learn? The learning is actually the weights and all that stuff, right? That is stored. So if you give the guy those weights again by using load here, then it will behave like this. One thing I will warn you against, I haven't done that, I tried it actually. If you resize the window, it will go okay for a while. But if you resize it in the wrong time, what will happen is that it will have an overflow, because it will think that it is exceeding the size that you reserved for it. That's a bug that's not fixed. Watch out for it. You will have to restart it otherwise. But we could do things like, let's see, I will draw a node for you here. Gosh, this is what I shouldn't have been doing. You see, that's how I discovered the bug. By chance, when you come to this site, you sort of take it. Yeah. Did you see what happened? Yeah, that's what I was thinking. Anyway, I knew that it would be the case, so this is what you do. You quit. Oops. Qui is not defined, of course it's not. Good, good, good. Where's your circle? He is your circle. Okay. And then, without coming very close to the load. Okay. I do this every time, sorry guys, and it's not going to do anything good unless this is the last bit, but it would be nice just to see how it does. Oh, shoot. I tell you, this code, if you really want to play around, has quite a lot of stuff that can be corrected. Oh my God. Load, load, load. Okay, then it starts behaving. I've loaded, and I'm rolling a nice little. See? It's a quick learner. So, I mean, and you can do things like, just to see how it behaves, you can just put some mess here. It's Oslo. There are lots of holes right after winter. It's getting a lot of punishment, okay? And then, if we say save again, you see that it is getting, this is probably when it crossed the line, and then this is probably when it came across that. So we see that it's sort of, it's a roundabout. It thinks it's going around it now. It's learned. See, and you see how it slows down when it goes into the, what I call the sand. Okay? That's the punishment response. Slowing down. The punishment is defined in the code relative to slowing down. That's more or less what it is. It's not the best of codes, not the most professional of codes, but it will give you a good idea about neural networks and pre-learning and deep pre-learning using neural networks. If you also do these exercises in the end, all right? Okay. Some homework is try to improve the code. You've seen that it's a mess. Experiment with different activation functions that Asgeir was mentioning. It is worth experimenting with a few because you will, even if it's not the best result you get, you will understand what they do. That is, okay? And not all functions are good in everything. So at least you will get an idea. Read PyTorch manual tutorials and or Google for alternatives. The PyTorch tutorial has all in the functional module. It has a good deal of most of the used functions, not all of them probably. But I don't know where the limit is, so I cannot judge. It won't be finding best path because we do not have the code for that, the optimization. Well, it sort of looks like it because we've been drawing some values, so that's why. But if you just let it go, it may take quite a long time before it finds it, or it may never find it. It may actually, in my case, just go around, touch home, and then go around like this, and touch work, and then go around like this. That's the longest path. So it's not optimized for the shortest path, not really. Okay? You can try to do that. And there are lots of optimization functions, by the way, as well, so you can look at it. But look at PyTorch. And if you really have more time than I usually do, look at TensorFlow as well, because there are lots of good stuff there. It is one of the most used libraries in Python. And it would be a good idea to have both, an idea about both. So, yeah, and tell me when you've done that. It's just a little thing that I want to show you before you go. And this is obligatory. You can't go anywhere before I show them. All right? Because this is the beautiful AI ML cloud artificial intelligence, machine learning cloud platform. You can try out for free. There was supposed to be some brochures there, $300 US free. Pick one of them if you want to try it. Because what you can get is Oracle's platform, both for relational structured data and unstructured data. You have a good deal of stuff that is in the form of advanced analytics, data manager, all that stuff, that's built into the database itself, and it is a very effective tool. And you have the equivalent in R built into Hadoop, basically. And then you have this platform cloud service. Instead of, if you have problems downloading and installing everything, this could be a good idea, but this is not released yet. It is announced, so it's coming around the corner. But corners can be relatively large in Oracle sometimes, especially when you're waiting for something desperately, so watch out. But this is the Python environment, and it is actually with the CUDA library for NVIDIA because the platform it runs on, the cloud platform it runs on, consists of GPUs, NVIDIA GPUs. You remember the CUDA stuff and the PyTorch stuff is made by NVIDIA. The PyTorch stuff is in cooperation with Facebook, but CUDA is pure NVIDIA. It's just for being able to run effectively in the cloud. And you have all the deep learning frameworks and libraries and tools, etc., etc. You have a lot of stuff, plus 25 giga Ethernet if you want to share that information. And practically nobody today uses only one cloud and one machine and one platform, so it's a good idea to have something that's effective that can work together with other things as well. And these are all the stuff. The Jupyter Pillow is the Python imaging library, and Pandas is a data structure library, etc., etc. You have OpenCV, which is a good one. It's not only Python, it's also Java, it's computer vision. And it's all the stuff that you, and there's the natural language toolkit as well. Practically everything that you would need for gathering data in, also from text or speech, and or pictures, being able to recognize pictures, patterns, that kind of stuff. All of them is there, plus all the translation stuff and everything that we've seen today, basically. It is an AI platform, cloud service. It's the other one that is also AI related is the conversational AI platform, which is the chatbot that people call a chatbot these days. There are several alternatives of a chatbot. This has natural language processing capabilities, but also deep learning capabilities. It's not only rule-based, because most of the chatbots are practical rules. So if you see this pattern, then answer this kind of stuff. You can do that yourself. Those are very simple. They are not really a learning platform, but this is much more learning platform. And I mentioned also some of the stuff which I just sort of jumped far too easily across. There's a tool here. If you go in, it's me. No, not any longer. Oracle data visualization is Oracle Analytics. There's an expert sitting right here, so I won't talk about it at this point. But that is a very good tool because it is sort of like a BI tool. You can do dashboards and visualizations based on data, but it's much more flexible. You can experiment with data, so it has discovery elements that will come and give you suggestions of how to visualize different things. And then you have all the necessary statistical tools that you can do visualizations with. But so it's a good data science platform, but it also gives you the ability of defining machine learning flows with the data input and a learning algorithm. Built in, you have anything from naive bias to God knows what else, all kinds of learning algorithms that you can use in your flow and generate an output in a clips instead of code. Right? Did I say anything correct?
Yes.
It doesn't. Sorry. But anyway, it's Kristen is here if you really want that. That is a good one, and play around with that because that gives you machine learning and statistics and visualization free almost without coding. It's just visual flows that we define. One of the things that we do is we have started play around with that as well. We have started putting, not giving you a development platform for using with Python or R or whatever, but we've started building machine learning into practically everything that exists. And what exists in Oracle, many people think it's only a database, but it isn't. You have practically all the applications that you can imagine, like CRM type of applications, or ERP type of applications, HCM type of applications. And you have middleware from 88 to O, C, since we're talking English. Okay, and we have the whole toolbox, basically. So everything is in the cloud. You have the bare metal that you can install stuff onto. You have the toolkit of Pythons and R's and God knows what. And you have the visualizers, etc., etc. Plus that you have, for example, that's in the analytics cloud with machine learning built into the visualizer or the BI platform, okay, analytics platform. But you can do things like play around eventually with databases that install themselves and tune themselves. They're autonomous. They have machine learning capabilities. So we're putting machine learning in every tool that we have, databases and middleware and yeah, whatever else, basically. And the most important one, because security is not man against machine any longer. Security attacks are machine attacks. So it's much faster than what a man can manage. So we built machine learning into our cloud security as well. Okay. There's also our data as a service that you can get, and lots of very funny, nice tools, applications Where are you? In standard apps, machine learning is built in so that you have in the customer experience, for example, a built-in smart offers and actions kind of stuff. In HCM, you would have best fit candidates. That would be if you're working with now, they're looking for this kind of stuff, matching the job offers to job seekers. That's perfect for that kind of stuff. And it has built-in machine learning. And if you have infrastructure management, that kind of stuff, these are just examples. I'm not going to go on with that, but this is, in a sense, it is a good thing to try out. You'll be surprised. And one of the things that I'm going to tell you now, which is illegal, and there are lots of managers and all that stuff to do behind that, but put your fingers in your ears, managers, I'm going to say it anyway. It's much cheaper than you would think. It's cheaper than Amazon, which means it's cheaper than machine learning. That's very surprising, because Oracle is not known as being the cheapest. But try it out. See how it works. And if you want any partner to try things out, if you get stuck, we're always here. You can contact me. Kristen is here, Frode is here. Of course, our managers, if we contact them first. That's a good idea. Anyway, thank you for your attention. That was the mandatory Oracle part of my presentation. But it is actually a good idea. Try it out, you will like it. Thank you.